Okay, so it's Friday of week 6, and next week is week 7, and we have a midterm exam planned for week 7 of next week. So I posted a document, midterm 2 topics. You know, I appreciate everybody who filled out the mid-quarter questionnaire survey, and just kind of let me know how you guys are doing. And it's, I think I had a suspicion that that things were hard this quarter, and basically the survey kind of confirmed that. And so I wanted to, be sensitive and be mindful of that while teaching the class. So I've decided to make a couple tweaks to the grading scheme. This is all with the intention of kind of easing student burden. And so this is what I've decided, and so this is reflected in the midterm 2 topics document. Okay, and and so what I've decided to do is, and this is not something I normally do. Okay, so normally I don't drop any of the homework assignment grades, um, but just kind of in light of everything that's going on, and just the difficulties of remote learning, I've decided I'm going to drop the lowest of the. There's going to be 6 homework assignments. I'm going to drop the lowest of them, and so your homework grade will be the average of the remaining 5 after we drop the lowest one. Okay, and with that in mind, I'm going to bump up the homework, the weight of the homework from 36% to 40%. Okay, and then I'm also going to reduce the weight of the final exam from 20% down to 15%. And I'm also going to try to target, when I write my final exam, I'm going to try to target it to be approximately similar to the midterm exams in terms of weight and length. Okay, so the first exam was 15% written for about an hour. The second exam also 15% written for about an hour. And then the final exam will also be around 15% written for about an hour. So the purpose of this is to kind of, I'm not trying to make the class easy, but I am trying to tone it down a little bit, right? So you can imagine me just turning a little knob a little bit for this quarter. This is not typical. Okay, normally I would not do something like this. So please don't tell other students that this is what I've done this quarter. If you enjoy the class, of course, feel free to give me a good review on Bruin Walk or whatever website you leave reviews at and stuff like that. But I would ask that you leave out the specifics of the grading scheme, because I don't intend to do this in future classes, and I don't want future classes to complain that their class is harder than the class that I taught in spring 2020, because students don't like it when they feel like they're getting something harder than normal. But anyway, I'm choosing to do that, based on the responses I got in the questionnaire, and I know for a lot of you, myself included, this is not an ideal situation. There's a lot more distractions at home. It's a lot harder to stay focused on your academics and things like that. So this is a change that I'm making, again, just for this class, because of the remote learning and the pandemic, and just the tough situation that we find ourselves in right now. So that's So I'll do that. I hope no one's opposed to these changes. This is all with the intention of easing your burden a little bit. Okay. And then regarding the exams themselves, for midterm 2, I'm also just turning the knob down a little bit to make the questions. Again, I don't want to say the questions aren't going to be easy, but easier than they typically are. Of course, you still should study and still prepare yourself for an exam. I'm going to use the same format that I did for the first midterm exam, which is that we are going to have a live exam. It's going to be live proctored via Zoom from 10 a.m. to 11 a.m. or 10 p.m. to 11 p.m. or 11:10 p.m. I guess, depending on which exam time period is more convenient or conducive for you. Okay, so same format as the first exam. Based on the questionnaire feedback, most students said that this exam format worked for them. A handful or a couple students did not like it, but I don't think I'll be able to find a solution that everybody is pleased with. But most were okay, and were agreeable to the format of the first midterm exam, of having a live exam time from for about an hour with about an hour of content. So that will be that. It'll be pen and paper again, and you will take pictures or scan it and upload your document to Gradescope, or if you have an iPad and you want to write on your iPad, that's also an option for you. But you can, all you need is paper and a way to take pictures of your exam, and I will provide all the details of the questions here. And again, this is not typical, and please don't share this document with other students or people who aren't in the class, or people who take the class in the future, because they probably won't get the exact same thing, and I don't want anybody in future classes to complain that their version of the test was harder than this one. Okay. Like the midterm, it's open note, open book, but no collaboration. So this is what we'll have. Okay, so your first question will be a numeric gradient calculation for a neural network. Okay, so I'm going to create a simple neural network. Okay, very simple. There will be 2 nodes in the input layer, 2 nodes in the hidden layer, and 1 node in the output layer. That's about as simple as we can get. And I will provide matrices for the first weight matrix, first bias values, second weight matrix, and second bias values. And to keep things easy, the activation function will just be the identity function, so you don't have to worry about any kind of transform, right? Whatever you get and you plug into the identity will be itself, so that's not going to change. Okay, and I will also provide the input matrix X, the actual values T, and I will go ahead and I will do the forward feed aspect that will produce the Y hat values. Okay, so so all of this will be done for you. All of this will be provided. So I'm pretty much describing the entire problem here. The only thing I'm not doing is giving you the actual numbers that go into the problem. But this is set up in a way that, as you study this week, this weekend and week, you can make your own example problems and try things out. Okay. So what you are going to do is you're going to calculate the loss value of the current parameter values. Okay, which will be kind of the sum of squared residuals, and then you will also need to perform numeric gradient calculation for one of the matrices, right? So what that looks like is you perturb, you add a small increment to each element in whichever matrix that we're talking about, you do it one at a time, and you see what kind of what change it has on the loss. Okay, and if you understand, you had to do this as part of your homework assignment on neural networks, and if you understand the steps that you wrote and did in that exercise, um, you should also be able to do it by hand if you were forced to do so here. Okay, and then you'll have a question that covers maximum likelihood and Fisher estimation. Um, if you look at lecture 5.1 with slides 13 through 19, there's a good example there. That is a Bernoulli problem, okay? Now the problem on the exam won't be Bernoulli, okay? I will provide a PDF or PMF of some distribution, but not the Bernoulli one, okay? And then I'll also provide some observations, and based on kind of the PDF I give and the observations that I provide, you're going to find the maximum likelihood estimate of the parameter based on the data. So, the idea there is you'll try to find a way to maximize the likelihood function by altering the unknown parameter values. Okay, so look at these slides. Okay, and then we'll also cover there's the second part of the question will be on Fisher information, and what you will do is you will find the Fisher information of the observed data. Okay, so that involves taking second derivatives and an expectation. So you'll do that, and you'll do it for the kind of the observed set of data that you have. So that will be that. There's also a Bayes classifier problem. Okay, a Bayes classifier problem. Again, you can look at these slides from lecture 6.1, and where the example I did there was you had bags coming from different factories, bags of marbles coming from different factories, and you had to guess based on the contents of one of those bags. You had to guess which factory it came from, and the problem will be kind of similar to that. Okay, and then you'll have a handful of conceptual questions. Okay, questions kind of from basically week 3 through maybe up through the naive Bayes classifier. So I guess lecture 3.1 up through lecture 6.2 as far as conceptual questions go. Okay, and those are always kind of a mixed bag of topics there. Okay, and this details out pretty much what I'm going to put on the exam. Again, this document is just for you guys for this quarter. Please don't post this or share this online or give it to other students, especially those who aren't in the class. It's always a little disheartening for me when I find my stuff on Campus Hero, or people copied and pasted stuff into Chegg and things like that. It's always disappointing to see that. So, so please don't do that. I think most of you will not, but it really only takes one student in the class to do something that breaks my heart here. So, are there any questions? Any questions about any of these changes or that I've made to the syllabus, or what is gonna what you'll see on the exam? Okay, no questions. All right. Okay, then I will. Then we'll go ahead and get started on. It says, are we allowed to use R for matrix multiplication? I'm going to say no. yeah. Uh, I mean, I don't know, like, yeah, it's open, no open book. I guess you can use your calculator, but yeah, I don't want people doing stuff on the thing. When will the homework scores come out? Yeah, yeah, I apologize. That's my bad. I'll follow up with the graders. You know, I'll always try to be fair as far as grading goes. So you know, if the homework scores come out and you feel like you were graded unfairly or something, you can contact me and we can try to work something out. But yeah, I'll follow up on the follow up with the graders on the homework to try to get your scores out. And I also know the midterm one scores still have not been posted. I will get those posted soon as well. I just feel like I'm buried in work right now, so I'm just trying to catch up and claw my way out at the moment. So um, please just be patient for the time being here. Okay, let's get started. As far as today's content, today's lecture is, I think, on the lighter side. So we are going to talk K-nearest neighbors. Okay, this is a classification algorithm. This is a way for us to classify classify a new observation. And the entirety of the algorithm is right here on this page, and it's quite simple. This is how the K-nearest neighbors algorithm works, also called KNN. Basically, you have training data, and in the training data, all of the data is labeled with a class. Okay, so data points will be labeled as one class or the other, and this is what you do. You get a new test case, okay, and you're going to measure the distance, generally the Euclidean distance, from the test case to every single other point in the training data set, okay? So this step can be very computationally expensive if you have like millions of data points in your training data set. You've got to calculate a million distances. So so it's costly. That step is very costly. So so for big data, almost no one uses K-nearest neighbors because it's too expensive to do. Also, as far as distance goes, distance is generally Euclidean distance. Is you do the difference in x1, you square that. The difference in x2, you square that. If you got other dimensions, you take the difference in x3, you square them, and then you add all of the squared differences, and you add them up, and you take the square root. That assumes you have numeric x variables, okay? And if x is your predictor variables are not numeric, you generally have to convert them to be numeric, okay? So, that's one reason why the iris data set is so popular, is because sepal length and petal length and sepal width and petal width, or whatever those are all numeric variables, and so they fit all of these algorithms very nicely and very cleanly. But if you have categorical data, you often have to find a way to make them numeric. That can be as simple as coding each category as 1 or 0, but in other cases it can be more complicated, and that falls under kind of the kind of branch of what we call feature engineering. We're not going to get into that in this class, but it's the idea of being able to build out numeric columns or numeric features based on other aspects in the data. So so if you have categorical data, you got to figure some way to represent them numerically. Okay, but anyway, once you have that, you're going to calculate the distance to every single other point, and then you sort. You sort all of the distances. You're going to sort them all, and then you're going to select the k observations with the smallest distances. Okay, and that's where the name KNearest Neighbors comes from, because the smallest distances are the nearest ones, and then you want k of them, so those are going to be your k-nearest observations or k-nearest neighbors. Okay, and then among the k-nearest neighbors, you're going to pick the class with the highest representation, right? So if you have k is 5 and 4 of them are class A and 1 is class B, then you're going to classify, for that test case, you're going to classify it to class A because most of the neighbors were of class A. Okay. The question is, how do you pick a k? How do you pick a k? Like, should you use k equal to 1, k equal to 20, something in between? We generally use cross-validation. So you'll, cross-validation, you set aside some of your data points to be a validation set. And then for each value in the validation set, you're gonna run the algorithm to see if to see how it classifies, and you're going to measure the performance and see how well or poorly it performs at different levels of k, and you'll try to choose your k using that. Sometimes you end up with ties. Okay, if there's only 2 classes and there are and k is odd, then no ties will result, and that's ideal, right? So yeah, what happens if there's a tie? Yeah, so we have a few strategies for resolving ties, especially if you have an odd number of classes, like if you have 3 classes, or not odd number, but more than 2 classes, you can end up with ties. So if you have 3 classes, let's say class A, B, and C, even with something like k equals 5, you can have 2 that get classified as A, 2 that gets classified as B, and 1 that gets classified as C. And in that case, you have a tie between class A and class B. Class A has 2, class B has 2, you've got a tie. So how do we resolve ties? There's no one rule, okay? These are just different strategies, and it's hard to say which one's gonna be the best, okay? So one option is you just say unclassified, okay? You just say, oh, there was a tie, I can't decide if it should be one or the other, okay? And that's fine, okay? Another is when you have a tie, you switch to the 1 nearest neighbor, okay? If you do 1 nearest neighbor, there is never going to be a tie. Another one is you select randomly among the top groups that are tied. So in our case where there was 5 observations, 2 are A, 2 are B, and 1 is C, you're just going to flip a coin between A and B because those had 2 those are tied for the most with 2 each. Okay. Or you can say among the 2 top tied groups, that is A and B are the ones that are represented the most, you're going to select the group that has the closest neighbor. Okay. And that could be different from the 1 nearest neighbor, because in a group of 5, it's possible if you have 2A, 2B, and 1C, it's possible that C is the closest neighbor. Okay, so if you used the 1 nearest neighbor, you could end up picking C. But if you just say, well, let's only limit ourselves to A and B, then you can pick the one with the closest neighbor between A and B. So these are all different ideas. None of these is best. Okay, that's just, these are different options that people have suggested for dealing with ties. Ideal situation is there aren't ties, but if you have more than 2 classes, then ties are definitely could happen. All right, I'm going to just generate some training data here, okay? And the training data looks like this, okay? And it's intentionally a mix, okay? The center of one is -1, 0, and the center of the other is 1.30. So one is centered over here and one is centered over here. but we just have some random points, and they're spread out like this. And if you just had to kind of pick, like, if you had to draw a boundary between red and blue, we might draw a line like this, like a simple boundary, but then this red dot would get classified on the wrong side if we draw a straight line here. But anyway, just kind of, in general, left side is blue, right side is red. But exactly where does this boundary exist? It's a little bit hard to say, right? So I could just draw a straight line, kind of like at 0 almost, and then I would misclassify red 1, and blue would get misclassified. But this is kind of what we have right now. All right, let's throw in a test case here. I'm going to throw in a test case right here at 0, 0, -1, and the question is, should this be a red dot or a blue dot? If we had to guess which class it was, red or blue. Okay, and I intentionally picked this because the answer is going to change depending on what K you pick. All right. So the K-nearest neighbors algorithm, what we're going to do is we're going to find the distances from this test case to every single other data point in the data set. Okay. So that's what this slide represents. We're calculating distance to every single other data point. And this would be represented in a matrix, not necessarily with all of these lines here. But that's what this represents. We calculate the distance to every single other data point, and then we sort them in order of closest to farthest, right? Minimum distance to greatest distance. Now, you might say, well, I can just look at this visually and say, I can tell you these dots here are the closest, and this dot and this dot, these ones out here are far away, okay? So in a 2D plot, our eyes are trained, and we can recognize distances very easily. But in higher dimensions, like let's say your data has 17 dimensions, okay? If you have 17 dimensions, then we are not capable of visualizing what distance looks like in 17 dimensions. Our brains can't handle that. What you end up having to do is you just have to go through the matrix, and you have to calculate the distance in 17 dimensions. And you have to do it for every single data point, because there's not going to be an easy way to just look at one observation and say, oh, this observation is going to have a huge distance compared to the other observations. It's going to be very difficult to tell. So yeah, it's going to be computationally expensive in that you have to calculate the distance to every single other data point. Okay, but yeah, for 2D we can visualize distances easily, but higher than 2 dimensions, it's hard. Okay, so if you have K equals 1 as represented by this red dot, the distance to this red dot's the closest, because if I draw a circle with this radius, no other dots are within the circle, so this is the dot that's the closest. It's going to get classified as red. The one nearest neighbor to the test case is red. If I pick K equals 3, the 3 nearest neighbors are these 3 dots, and out of the 3, 2 are red and 1 is blue, and so we're going to pick red again. We're going to classify as red. If I choose K equals 5, then out of the 5 nearest neighbors, 3 of them are blue and 2 are red. So with K equals 5, this dot's going to actually get classified as blue. And then with K equals 7, these are the 7 nearest. This dot is very close, but it's not quite close enough, okay? So with 7, we've got 4 that are blue, 3 that are red, and so this dot's going to get classified as blue with K equals 7. Okay, is that all right for how the algorithm works? Let me give you your first quiz answer. First quiz answer is D. D as in dog. D as in dog. Okay, so that's it. Let me just show you a couple more, another example here. Okay, here I'm going to put a test case right here at 1, 1, and so what we do is we start off by measuring the distance from this dot to every single other data set data point and the training data. And then from there, we're gonna sort them. Okay. If you had to guess, what would you classify this as? Okay, I think we would agree that this dot should be red. And let's see how the classifier works. Okay, so here's the distances, and let's just see, right? So at k equals 1, the nearest one is red. At k equals 3, we have, these are the 3 nearest neighbors. 2 are red and 1 is blue, so it's still red. At k equals 5, the 5 nearest neighbors, of those 3 are red and 2 are blue, so we would rate this as red, okay? And then here with k equals 7, it's still red, 4 are red and 3 are blue. We still classify as red, okay? So as I include more data points, it still remains red. Okay, I've got a bunch of graphs here, and I copied most of this from Stack Exchange. And I should probably resize it so you can see it. But here is this is the same data. If you pay attention and look for like kind of these patterns of blue and red dots, it's the exact same data here. Okay, and what I've done is I've drawn a boundary region based on k equals 1. If we use k equals 1 neighbor, this ends up being the boundary region. Okay, now this doesn't look all that strange, but if you think about it, right, if we only looked at this and I said draw a boundary region, I don't know if we would try to draw our boundary to make sure we don't misclassify this dot, okay? But that's what k equals 1 will do. K equals 1, every single dot gets basically its own boundary zone, and so the algorithm worked hard to kind of draw a the boundary to include this here. Okay. As I increase k, what's going to happen? The word isn't that the boundary gets smoother, but in general, the boundary will get less influenced by just one unusual observation. So there's one observation out here I would say is fairly unusual, probably should be a blue dot, but for whatever reason in our training data, it is a red dot. And when you increase k, the boundary is going to get less influenced by any kind of one dot that's way out there, right? Also, this blue dot, you know, is kind of in the red zone. So as I increase k, what's going to happen is the boundary is less influenced by, you know, any one dot, and we get kind of a, this is what the boundary looks like. And as I increase k, again, the boundary gets less influenced by any kind of observation that's a little bit out there compared to the other things, okay? And here it is with k equals 7. So that's what we have there. K equals 1. Every k equals 1 will have basically no misclassifications on the training data, but it's generally going to overfit. It's going to overfit the training data. And k equals, as k increases, the boundaries are less influenced by any one point. Now, if you max out k to some number, right, then the number of observations you have in the data set will make a difference. Like, so for example, if I don't have this in this data set, but if I had like 20 blue dots and 15 red dots, and if I picked k equals 35, with 20 blue and 15 red, blue is always going to win 20 to 15. And so with k equal to 35, the whole zone will be blue, which is undesirable. Okay. Okay, here is another data set, more data, purposely kind of messy. And the question is, where is the red and the blue boundaries, right? So this blue dot is definitely in the red zone. This red dot over here is definitely in the blue zone. And then these ones are a little bit, should these be red? Should these be blue? It's a little bit strange, but generally, blue on the left, red on the right, but we have some kind of unusual dots here and there. So where do they go and how should we classify all this? Okay. With k equals 1, this is what we get. No misclassifications in the training data, and everything that's a little bit strange basically gets its own little enclave. It gets its own little small territory, right? So here is this blue dot gets its own little island, okay? And this red dot gets its own little island. It's kind of like what's a country with a little enclave, right? Like the United Kingdom has the Strait of Gibraltar. What is that?
Swaziland in South Africa.
Does Swaziland have something like that? There's Lesotho in South Africa. That's it. But it like Lesotho is its own nation. But this is like what do you call it? So like if you look here, this is completely unrelated, but Strait of Gibraltar. Yeah, Russia has land in Poland, and then as far as the Strait of Gibraltar, it's like all Spain, but then but this right here, this is part of Britain, I think. No, so there are like city-states but I'm saying this is like blue country, but then they've like staked out their own little land in this is not like its own country. It's like Gibraltar, British Overseas Territory. Like you think this should belong to Spain, but guess what? The UK owns it. So kind of yeah. But anyway, all of these things get their own territories, right? And we're obviously overfitting. We're overfitting. Okay, this should be red. Okay, but like any reasonable person would classify this as red. So with k equals 1, that's what you get. Okay, as you bump up your k's, okay, here we have k equal to 3. These things no longer get classified. Okay, coincidentally, this zone happens to end up getting classified blue, even though there's a red dot there, and that's just like a coincidence of these two blue dots kind of influencing what ends up happening here. But and also these 3 red dots end up in the blue zone. But as when you increase k, these one-off observations that are off in the middle of nowhere or in the wrong side don't influence the boundary regions as much. Okay, and as I increase my k, again, the word isn't that the boundary gets smoother, but again, they get less influenced by 1 or 2 straggling observations. So here's k equals 5, here's k equals 7, and if I crank this all the way up to k equal to 20, you get kind of this, again, a boundary that's less influenced by crazy one-off observations that are often the quote unquote wrong territory. In general, though, as you increase k, what happens is you get higher bias, lower variance, okay? And then with k equal to 1, you get low bias, high variance, okay? So with k equal to 1, in the long run, the zones will get classified correctly in the long run. But for any one data set, it's going to be heavily influenced by the random observations that you see. So k equals 1, low bias, high variance, k big number, okay? And big number is relative to the data points that you have. K big number will be high bias, low variance, okay? Again, because of this step, in the algorithm that you have to measure the distance to every single other point in the training data, this is a very computationally expensive data set, especially if you have a big data set, right? If you have 1,000,000 observations in your training data, you've got to calculate 1,000,000 distances, which is a lot of computation to do. So, so K-nearest neighbors is not popular in big data contexts. Okay, so if you have a large data set, KNN is generally not used. But you know, I would say less than 10,000 observations or something, sure, KNN could work. But if you're in the order of hundreds of thousands, millions of observations, KNN is not preferred. R implements KNN using this KNN function, but in your homework, your coming homework assignment, which I will post and release, I will have you code up the KNN algorithm yourself, okay? And again, the algorithm itself is fairly simple, and you will code this up yourself, and I think it will help you solidify your understanding of the K-nearest neighbors algorithm. In case in an interview they ask you to whiteboard out K-nearest neighbors, you can explain it very well. And so you'll have to think about how to write your code and implement it that way. And that will be in a coming homework assignment. Okay, that's all I've got for you guys today. So we'll end here and have a good weekend, and we will see you guys on, oh, second quiz answer. Thank you for that reminder. Second quiz answer is B as in boy. B as in boy, B as in bear, Bruin. I don't know what else is a B word. Bears beats Battlestar Galactica, right? That's okay. So we'll end there and have a good weekend. We'll see you guys on Monday.